Okay, so this is one of the questions that I haven't yet done that I really should finish. I did a similar kind of question as this one. It involved the heat engine cycle, and it involved isochoric heating and isobaric contraction. So let me sketch it so that I don't have to keep all this in my head. So in a PV diagram, we plot changes of pressure and volume. So there's isochoric heating that would be constant volume, increase in pressure as you heat it up. And then it ends up with the isobaric contraction that would be reaching this point with the heat leaving at a constant pressure, isobaric, and until it reaches this volume. And this is the part that would be different from the other question I've done. The other question, this was adiabatic expansion. Now this is an isothermal expansion. Now you wouldn't really be able to tell that in a sketch. In a sketch, both isothermal and adiabatic looks like a curvy thing that looks like a 1 over r, 1 over x kind of shape. But what's important here is that here the temperature T is constant. That's what isothermal process means. In an adiabatic process, instead of the temperature being constant, you have there being no heat transfer. Here, there will definitely be heat transfer in as the gas expands, so that its temperature can stay the same. Temperature staying the same means the internal energy stays the same through the first law of thermodynamics, which, as a reminder, says first law, change of internal energy of object, of a thermodynamic system is given by two different sources that could change internal energy. The net heat transfer minus work done by the system. And different disciplines use different conventions. In physics, whenever we talk about work, we are really talking about work done by the system, not on the system. And that matches this minus sign here. I think in chemistry, sometimes you talk about the work being done on the system. So this sign would be positive. So as the gas undergoes this isothermal expansion, it's doing work. There's area under the curve. And in order for the temperature not to change, which it's a monatomic ideal gas, so this change of internal energy would be related to 3/2 and kb times change of temperature. So temperature not changing means internal energy not changing. And for that to happen, you need to have net heat transfer basically being equal to work being done. So that's the isothermal kind of condition or things going on with the isothermal process that you should understand as you approach this question. So let's label a few things here. It says the initial state just prior to isochoric heating is at a, let's label this, at a 120 kilopascal at a volume 0.045 cubic meter. Isochoric heating increases the pressure to 890 kilopascal, and we can work out other parameters like temperature using the ideal gas law, which I should probably write down. Ideal gas law says pressure times volume is equal to number of molecules times Boltzmann constant times T. We'll probably using a version of that, and then I think with the isothermal expansion, I can work out this volume if I ever need to through the ratio of the pressures. And with the isothermal expansion, it has to complete the cycle. Answer below questions. Okay, so it asks, what is the heat input over one cycle of the heat engine? Oh, yeah, so I gotta basically work it out for the entire cycle before I can answer any one of these. You know, some multiple choice questions are written in a way where it kind of builds up. Here, it's not written that way. You just have to work it all out. So this is the process 1, process 2, isothermal, and then process 3. So let's just work it all out, and then we'll just do all the parts all at once. So the and let me label the vortices A, B, C. So the process 1, which takes you from A to B, as the question said, it's isochoric heating. So it being isochoric process actually tells you one thing right away. Isochoric means change in volume is 0. So that means work being done is 0 right away. So you can immediately get that change of internal energy all comes from heat transfer. Let me label this Q1. Okay, and I think I can write down change of internal energy from this expression here. So change of internal energy will be 3/2 kB times delta T. Now you might think, but I don't know the temperatures either at A or B. This is where the ideal gas law is useful. Let me express it in terms of change of temperature. So expressing it that way, I would say N kB times the change of temperature. And to be perfectly correct every single time, I would have to say change of P times V. Sometimes one of those two will be constant, will make my job easy, but not always. And I'm noticing one mistake I made here. Let me fix that now. That's what was distracting me. I forgot N here. For the total internal energy, I would need to put in N there. So N kB delta T. So you can see that I have a very useful expression here, N kB delta T. So I can just plug it in here and basically get change of internal energy, which also gives me the heat transfer into the system, is 3/2 times this, or that, which is that. Change of P times V. Or in terms of the quantities we have, let's label this P A, V A, and label this PB. And V stayed at VA, so it'll be 3/2. So this is a change of pressure times volume. I can write this simplified version. The change of pressure, PB minus PA, times the constant volume. You can imagine that I did the final PV minus initial PV and then factor out the constant V. Okay, so that's I think that gives me all the parameters for this process. In each of the steps, I'm basically looking for each of these parameters in the first law. Change of internal energy, heat transfer, work done. I got work done, change of internal energy, which is the same as heat transfer, which is this quantity, which can be expressed in terms of everything I already know. Good. Let's do step number 2. Process from B to C. So this is the process that's different from that other question. In the other question, it was adiabatic. I could say heat transfer is 0. Here it's not. Instead, what I can say here is from being isothermal, I can say change of internal energy is 0, which means the heat transfer, Q2, minus the work done in this step is equal to 0. Or put it another way, I can get heat transfer as work done. So it's this work done part that I need to calculate. I guess your textbook does derive the work done in an isothermal process. If you want to use that, that's fine. Let me just practice what I preach for once and just quickly derive that. So work done during an isothermal process is going to be, you have to first start by expressing it as infinitesimal amount of work being done. So that's going to be amount of pressure times infinitesimal volume change, integrate over the whole process, I guess. So here, let me just be correct and say it's going to be from B to C. B to C. So this is the schematic representation of what we are doing. And in order for us to actually do this integral, I really need to rewrite P in terms of V. Is that what I want to do? Yeah, let's do that first. That's because that's the kind of standard way to do it. So I'm using PV is equal to NKBT. Solve this for P. P is equal to NkBT divided by V. So this pressure is equal to NkB. You know, T, I don't know what that T is. Let me just say T B for now. Divided by, and V is going to be a variable. So V. So let's write this out. This integral written fully out. So the value of V is going to go from volume at V, volume at B, which is the same as a VA to VC, which we do need to figure it out. I'll quickly write it out after I write down the integral. So it's gonna be NkB TB divided by V dV. And I guess I could do the integral now. Let me do some simplifications. So this VC right now is another unknown, and I really don't want to have a lot of unknowns. So this is where we use the fact that it's an isothermal process, and with the isothermal process, this is what you can write. You can write at the beginning of the process, PBVB is equal to NkBTB. This is equal to NkB temperature at the final step, C, which through the ideal gas law is equal to pressure at C times volume at C. So through transitive property, these two are equal to each other. So VC, I could write that as doing the algebra in my head, PB over PC times VB. Now this is where the PB diagram is helpful. Looking at the PB diagram, you can see that pressure at C is the pressure at A. So I can simply write this as PB over PA times VB. Which VB is VA. Because A to B, again, referring to PV diagram, A to B, volume doesn't change. So VB is VA. So this VC, I can now rewrite that as the ratio PB over PA times VA. And I'm hoping VA will somehow cancel out somewhere. Let's just work through and see. And one other kind of simplification I can do. So this NkBT expression here, which is also here, it was equal to PB times VB, which is the same as PB times VA for the reasons we were saying earlier. So I'm just gonna plug this in. I think basically I don't think I need to look up Boltzmann constant. I can re-express everything in terms of pressure and volume, and I don't need to deal with the Boltzmann constant or possibly not even temperature. So PB times VA divided by V dV. All right, that's probably enough. Let's do the integral. All these are constant. I'm gonna pull it out of the integral. PB VA divided by, that's not constant. So I have 1 over V dV. Antiderivative for that is natural log of V. Just double check it by taking derivative of natural log of V with respect to V. You get 1 over V. Evaluated from VA to PB over PA VA. All right, let's carry on. PB VA. So the evaluating at these two limits, natural log of PB over PA VA minus natural log of VA. And this is where knowing a little bit about logarithm algebra helps. Because logarithm algebra, like natural log of A minus, let's say a minus, natural log of B is equal to natural log of A over B. When you're plugging numbers, maybe it doesn't matter, it doesn't help all that much. But with the terms like these, if you can put it in that form, then you can see this very convenient cancellation. Natural log of PB over PA times VA divided by VA. So VA's cancel out, and you get this super simple expression for the work done in process 2 PB times VA times natural log of PB over PA. And we can, this is all in terms of numbers we have. Very simple. Let me copy this up and organize my work so that I have space to write the rest of the stuff. All right, so that's process 2, I think. I worked out the amount of work being done, and that will also give me the heat transfer and the change of internal energy is 0, and that's the 3 quantities in first law. Let's finally wrap up with the process 3, the isobaric contraction. So, process 3, going from vertex C to A. So in isobaric contraction, I guess in some way it's kind of more complicated. You just have to work out the amount of work being done and the heat change of internal energy, which will give you the heat transfer. So you rewrite the first law into this form. The heat transfer in process 3 is equal to the change of internal energy in this process plus work being done in this process. So in some sense, it's kind of more complicated than the other of the two that we've been dealing with. But each of these parts are kind of simple. So work being done in step number 3, it's really this area under the curve, the rectangular area under the curve. So it's easy, P times delta V. So let's write that down. It's gonna be pressure, PA, times delta V. VC minus VA. Oh, and I think I worked this out before, right? I worked out VC here, PB over PA times VA. So plugging that in, I have, and doing some algebra. Well, let's not do too much algebra in my head. So PA times, I'm going to factor out VA after doing the substitution. Then I have PB over PA minus 1. And I can actually do one more step of simplification, multiply PA into this part, distributing it in. Then you get this. VA still outside times PA here cancels, so I get PB minus PA times 1, PA. So beautiful. That's the amount of work being done. And for change of internal energy, we use ideal gas law. So we use equipartition theorem, which says change of internal energies for monatomic gas, 3/2 NkB change of temperature. Now using ideal gas law, you can say this portion is delta P times V, 3/2 delta P times V. So with all this in mind, then what I'm writing is for change of internal energy in process 3, is 3/2 times, I think this delta PV, that is what I calculated here basically. So I can just reuse that. Let's use this expression, which is the simplest. So I'll just write down VA times PB minus PA. All right, that's the last of the steps. Let's organize all this info. So for part A, it's asking for what is the heat input over one cycle. And I've done all the work. Let me just highlight where I'm getting it from after erasing some of the confusing highlights. So the heat input over one cycle of the heat engine. I have heat input here, Q1. And I have heat input here, Q2, which is the same as this. And in process 3, this wouldn't be heat input. It would be heat output, heat loss, so waste heat. So for part A, I just need to add these two. So let's just write that up. 3/2 PB minus P A times VA plus PB times VA times natural log of PB over PA. But will it simplify? I don't think it really simplifies. So I just need to plug in the numbers. Let's do that. So I have 3 halves PB, which is 890 kilopascal minus 120 kilopascal times VA 0.045 meter cube plus PB, which is 890 kilopascal times VA 0.045 meter cube times natural log of, I can just skip the units, PB 890 divided by PA 120. Units will just cancel. So that should give me some numerical value in kilojoules. Kilojoules 132. Let's hope that this is correct. Good. Let's keep going. It asks what is the net work being done by the engine. So for the network, again, I've done all the hard work already. I just need to find the right quantities to plug in. Let me delete the previous highlights. So for the process A to B, there's no work done, so 0 work. I'm doing positive work into as it expands. I already calculated that. Now in process step number 3, I'm doing negative work. And I think that might already be built into the expression. Let's just see. So really I should have had minus sign here because I wrote this as a kind of positive number. And in process number 3, you will do negative work. So I need to make sure that I remember this minus sign. So remembering the minus sign, the work being done in the entire cycle is W2 PB VA times natural log of PB over PA, and then minus the positive quantity VA times PB minus PA. And again, it won't really simplify. So let's plug in the numbers. So plugging the numbers. I think I can reuse a lot of this. So PB times VA, this is that. So we are using this minus. Now there's no more 3 half. I have PB minus PA times VA. Yeah, great. Got rid of the 3 half. That'll give me 46 kilojoule of work done. Okay, waste heat over 1 cycle. So for the waste heat over 1 cycle, there's a couple different ways you can do it. You can do it the way we've been doing, identify the heat output. So I guess here it would be this here. We can work this out and then enter that. That's one way to do it. Let me show you a much quicker, much easier way to do it. It uses the fact that this entire process is cyclical. So after a one whole cycle, like if you started from here, then after one entire cycle, the change of net internal energy is 0. You come back to the same internal energy. And we've tracked 2 different change of energy of the heat input and the net work done. And this waste heat basically has to be that thing that brings everything into balance, where when you add up all the energy changes, the total energy change when you come back here is 0. So this QL here, it should simply be QH minus W net. It's a lot simpler calculation than what we would do plugging in all these numbers once we've already done parts A and B. So let's do that. So, I think I can do this in my head. So it's 86 kilojoule. Wow, that is a lot of waste heat. So the efficiency is defined as that. So you just do that 46 divided by 132. Wow, that's 1/3. So that should be 0.33. I think. Yeah, sorry, that's a trap for me. Isn't that 1/3? No, yeah, it's not 1/3. Yeah. Let's use calculator. So 46 divided by 132. It's close to 1/3, but it's not quite. It's off by enough. 0.348. Off by enough that it won't grade my previous answer is correct. So yeah, that's the other cycle involving isothermal expansion instead of the adiabatic expansion that the other question involved. And yeah, looking at the time, it's a long process, and I would say what my goal for you is to be so practiced in questions of this type that exercise like this should really become tedious, boring, but not difficult. It is, tedious and boring in that it's multi-step. There are a lot of things that you have to remember and multiple steps you have to go through, but it's the same step for every single thermodynamic process question. So each of these steps are relatively easy. Piecing them all together, it's complex, but it's each easy link in the chain, each link in the chain. So my goal for you is for working out questions like this to be tedious instead of daunting and difficult.